The flux form of Green's theorem still relates a line integral to a double integral of the area of the region. The important thing to notice is that for your vector value function, you're doing the flux calculation for the line integral, which means that you're taking the dot product of your vector value function with the normal vector to the curve. This gives you the total amount of vectors in the direction of the normal curve. The double integral is like the total rate of change of your vector value functions within the area of the region. You can interpret this flux form as telling you that if you want to know the total amount of change within the region, it's equal to just counting out where the vectors are going along the border of the region. At quick glance, you can see that for the area side of the Green's theorem, we're taking the partial derivative of our vector value functions with respect to the components they're already in, and then we're also adding them. And when we do the dot product on the other side for the line integral, you have to find the normal vector. And actually, we have a simpler version of this expression earlier in the section when we calculate the flux, or the previous section. Let's take a look at this example over here. First, we want to take a look at the region that we're looking at for this calculation, and it is the unit circle, so that is a circle of radius 1, center at the origin. That's the region inside, and the circle's over here. I'm going to give the standard parameterization for that circle. So I happen to remember if I want to describe this unit circle as a parameterized curve, a good choice is to set my x-coordinate equal to cosine of t and my y-coordinate equal to sine of t. I let my time parameter go from 0 to 2 pi. That would give me one rotation going counterclockwise. If I were to use the line integral calculation to find this answer, I would use this parameterized vector value function curve over here. I would find the normal vector to that vector value function over here, which means in a two-dimensional plane, you're switching the x and y coordinates and flipping the sign of whatever is inside the y coordinate. But instead, I want to use the other side of the theorem, which tells me this formula is I take my x component of my vector value function, take the partial derivative with respect to x, give me this 3x squared. I do the same thing for my y component, so they take the partial derivative with respect to y, and that gives me this 3y squared. I substitute those calculations into the appropriate part of the formula, and now I have to work out my limits of integration. I've chosen to do this particular function in polar coordinates because the region and the expression becomes really easy to see or to compute in polar coordinates. In particular, if it's polar coordinates, my x is replaced with an r cosine of theta, and my y is replaced with an r sine of theta. When I substitute those expressions into the x squared and y squared, I get r squared cosine theta, r squared sine theta. I can factor out the r squared, and that really means cosine squared plus sine squared, which we know is 1 by now. Oh, I forgot to put parentheses here. In polar coordinates, a region of a circle is really easy to express because I'm going to integrate with respect to the radius first, and starting from the origin, working my way out, I can see that over this region, my radius goes from 0 all the way up to the edge of that unit circle, which is just 1. When I move on to my d theta, my angle sweeps around from the positive x-axis all the way back to the positive x-axis. That's a full rotation, so 0 to 2 pi. The first integral is just power rule with respect to dr, which is why I get r to the fourth divided by 4. I plug my limits of integration. That gives me the 1/4, which reduces this expression down to 3 over 4. And now I do my integral again. This is a constant, so it really just going to be times my limits of integration, which results in 3 pi over 2. So the total flux around this unit circle done by this particular kind of vector field is this 3 pi over 2.